Welcome guys to lecture 6. This is Dr. Wael Abu Saadat. I hope you're doing well, you're keeping your social distance, enjoying your masks. And by the way, masks are not enjoyable. You know, when you keep them on your face for like few hours, you feel like you're in the swamps on the Amazon. Anyway, let's start the lecture. I hope you're having fun. You're listening to this lecture on the beach. I'm not sure how enjoyable I am going to be if you're sitting on the beach, but at least you have a nice scenery in front of you. So the data structure we're going to look at today is called quad trees. This is a very, very popular data structure, not just used in indexing inside database engines, but actually it has all kinds of usages, okay? Including in graphics, for example, it's being used, including in AI, it's being used, including in machine learning, it's being used. And it's getting so popular to the point that when I was preparing the lectures, actually, the lecture for today, I came across an article in Science Direct, believe it or not, that talks about quad trees, okay? So it's a very interesting data structure, you know, because Science Direct is really not about programming or software, it's more about biology, physics, and medicine. But even then, even there, you know, they kind of got interested in this notion of quad trees. So quad trees are actually built on the pyramid structure, okay? If you have got exposed to this before in terms of, you know, the pyramid structure, most likely it was in your geometry class, perhaps in grade 3 or 4 in your elementary school, when your math teacher tried to make you interested in geometry, okay? So how do you draw a pyramid? This is how you do it. You start by plotting or drawing level 0, which is going to be the top of the pyramid, and then you draw basically a square, and then you immediately under the center of that square you draw 4 more squares, as if you've split this square in level 0 to 4 ones in level 1. And then you keep doing that, splitting each one of the 4 squares into 4 more squares, so now you have 16 squares, okay? And you can keep doing that until you get tired, and then finally you connect the edges or the corners of the squares across all levels. And this is how you actually draw a pyramid, okay? A geometrically correct pyramid, like the one in front of you here in the slide. Now, mathematically, we're interested, and this is really where quad trees will, this is how it will be built. We're interested in the number of squares in every level. So in level 0, and we will express them all the time as a power of 2 for simplicity. So in level 0, it's going to be 1 square. In level 2, it's going to be 4 squares because I split the 1 into 4. And in level 2, I split the 4 into each one of the 4 into 4, so that's 16. So mathematically, you know, it's going to be 2 raised to the power of the level multiplied by 2 raised to the power of the level. Okay? Now, you can plug in the numbers here and you will believe me. Like if you say 2 to the 1 multiplied by 2 to the 1, that's 4, which is exactly what you have in front of you in level 1, where 1 is the level number, assuming that I always start from level 0. Now, level 2 is going to be 2 to the 2 multiplied by 2 to the 2, which is 4 by 4, which is 16, which makes sense. If you split each of the 4 to 4, then you got 4 by 4, which is 16. Okay? This is how we think of quad trees. This nesting structure that goes from top to bottom is basically the same kind of merit behind constructing a quad tree. And you will see why it's, you know, useful shortly. So before I show you the example of a quad tree, I would like to tell you that actually this way of thinking in 2D will produce to you what we call a quad tree. But you could also imagine, if you can, it being done in 3D. And if it's done in 3D, it's going to be called an oct tree. This is also another very popular data structure in the graphics world. Okay, used a lot to actually present scenes and do manipulations inside a scene. But I will, strict myself here to quad trees because this is what gets used inside database engines. But everything we talk about here is applicable in the 3rd dimension if we are interested to use it in the 3rd dimension. Now, again, this is a 4-layer pyramid, okay? What we're doing, we have these layers that start from level 0, or layer 0, all the way to layer n. And we can easily determine the number of squares in every one of the layers, as I already mentioned, using this simple formulation, which is 2 to the power of the level multiplied by 2 to the power of the level. Now, what's interesting about this structure? Why are we talking about it, and why it's getting so much attention? Actually, it is getting a lot of attention, and people are finding a lot of usages for it because of its simplicity, because of the systematic way of creating it. It will turn out to be actually such a great idea to work with when you are trying to narrow down your search space as fast as possible without having to spend time to find how you split the data you're working with. Remember, we faced something similar to this before when we talked about the grid index. We said that the problem with the grid index is finding the appropriate ranges to split the data evenly between all the cells of the grid. So it turns out actually that quad trees solve the problem for us in an incredibly simple way, okay? And you will see how that is achieved. So let's talk about partitioning in the quad tree. What we have are squares of fixed size. But as we go down one level in the tree, for example, from level 2 to level 3, as this illustration shows, what we are doing is that we are splitting each one of those squares in level 2 to 4 squares in level 3. The impact of that is that we are actually enhancing the resolution of the X data set that was contained in the top left square in level 2 by splitting it into 4 squares in level 3. Okay? Now remember that the levels are centered. That's why I have placed a red dot here, because you could imagine level 2 is centered on the top of level 3, so the 2 red dots align on the y-axis or on the vertical axis. But the resolution now has changed. Level 3 provides us with a better resolution because it has more squares, if we just think of the X data set. And we will apply the same idea on the other squares, of course. Okay? So we say that the partitioning works like this. Every element is parted or divided into equal size elements that exist in the level below it. And there is a one-to-one mapping between the locations. So X was top left, and the 4 splits that we made out of X is also in the top left in level 3. So here's an example of a quad tree construction. I want you first to look at the left, and let's imagine that this is a map without any vertical or horizontal lines. We just have this map with the X and Y axis that stretches from 0 to 127 in the X axis, and similarly in the Y axis, and we have these points scattered around, A, B, C, D, E, and F. What we're going to do is that I will imagine that the map itself is a big quadrant, which is going to be level 0 in the pyramid. And then I will split that into 4 quadrants. Now, 4 equal quadrants. So here the splitting is straightforward. I'm just going to divide 127, the maximum coordinates, by 2. Integer division, I get a point and I draw a line. Splitting vertically, and the same thing splitting horizontally. Now this is, as you noticed, is much easier than what we have seen with the grid index, which created all kind of trouble for us when we tried to actually find out where should we draw the line, where should we split, or basically the regions that we talked about, and we said that this can only be identified optimally using a dynamic programming algorithm design technique. But here the splitting is straightforward. I just find the midpoint and split. Now the question is, how far can I go in the splitting? And here is the rule for quad trees. We will continue splitting until the quadrant is either empty or contains 1 point. So after I have drawn the first vertical and horizontal line to split it into 4 big quadrants, I will check every quadrant what's inside. Well, top left quadrant has A. It's only 1 point, so I'm not going to split that further. Bottom That's top left. And then bottom left has B, only 1 point. So I'm not going to split that further. Now, top right has C and D. Here are 2 points. And we said we will stop when the quadrant is empty or it has only 1 point. So I will split that top right quadrant, again using the same strategy. And now I have in the top right quadrant 4 nested quadrants. One has C, one has D, and the other 2 is empty, so I'm not going to split them. I go to the bottom right quadrant. It has E and F. That's 2 points. Again, we're going to stop when the quadrant is empty or it has 1 point. So I split that further. Now, when I do that, I will find that 3 of the quadrants are empty, but the top left in the bottom right quadrant, which has E and F, there are 2 points. So I split that further. So now I have E in one quadrant and F in another quadrant. Then I don't need to do any further splits. Okay? Notice that this data structure is great for processing spatial data, because spatial data is associated with location. It's about locations. Locations is on a map, so I can get the points on the map and then start to do what I'm describing now. Now, this is not the quad tree. These are just the splits. From what we have just done from this exercise, we will construct the quad tree, which appears on the right side. Now, the quad tree, as a rule, every node will have 4 children or 0 children if there is no children. Okay? There is no intermediate possibilities. Okay? So if we start from the root, we made 4 splits for the 4 big quadrants we created, and that's why you see 4 children to the root. Now, if we're not going to split the quadrant further, we just put the data point inside it with its coordinates. If we're going to split the quadrant further, then we put an intermediate node, which is denoted here as a circle, and then we continue on splitting by having 4 children for that node that we inserted. Okay? Which is, for example, here, the second child to the left of the root. Okay? Which is labeled NE. So usually these 4 children will always be labeled by their location: northwest, northeast, southwest, and southeast. Okay? And as you notice here, the B is actually has no children. That's why it's a square. This is a data point, because we don't need to split further. But the southeast had to be split several times because of D and F, which I already described. So the quad tree is actually what will show up on what is showing up here on the right of the slide. Now, if I would like to do an insertion, let's say I would like to insert a new point that will come beside the B, in the same quadrant as the B, that will cause a new circle or a new quadrant to be inserted instead of the B, and then that will have 4 children. One of them will have the B, and then the other new point will be in some other subquadrant. Okay? Now we come to the question, like, how we insertion this. And when you go in, because of our systematic division at the midpoint, you are going to compare coordinates. So let's say, for example, you're looking for the C. You would like to know if C exists or not. Okay? Or you would like to know what exists in the quadrant that has the C. So you find out it's actually the C. Now you must go in this data structure with some coordinates. Okay? For example, if you are looking for what exists at the point where C is, so you must go in with the coordinates 70 and 10. Okay? Now, associated with every one of the children is the boundaries, x1, y1, x2, y2. Where is this on the map? Okay? And in fact, you don't even have to store it. What you need to store, actually, if you would like to be a little bit optimal, is just the total size of the map. Because at the first level, at level 1, level 0 is the root, at level 1, you're going to split evenly the total space into 4 quadrants. So where it says A, I don't even need to store what is x1, y1, x2, y2, is going to be 0, 0, which is top left, and the midpoint of 127 divided by 2, so that's going to be about 63.5, or let's say like 63. So it's going to be 0, 0, and then 63, 63, which is the center of this map. Okay? Or 63.5, 63.5, which is the center of the map. So I don't even need to store the coordinates of these quadrants. It's systematically divided, you know. And if I would have divided the quadrant that has the A into 4 quadrants, I know the outside is 0, 0, 63, 63, so I'm going to split that. It's going to be, the first one is going to be top left, is going to be 0, 0, and then it divides 63 by 2, so that's about, you know, 31.5. So it's going to be 0, 0, 31.5, 31.5. So again, here, because the divisions are systematic, I don't even need to store the coordinates, okay? And just like I have found a place where to put something by, you know, comparing its coordinates with the quadrant coordinates, when I'm searching, I'm going to do the same. Okay? If I would like to know, for example, what exists in 63, 0, 63, and 127, 127, which is the lower half, then I can find that immediately from the quad tree by just going through the right subtree and retrieving all the data points there. So again, this is gaining popularity because of this. It's super simple to work with. It's you know, analogous in its simplicity to the bitmap index. It's the same level of simplicity. Super simple, super fast, and you can get the result, you know, without a lot of manipulations, basically. Now, who uses quad trees? Again, Postgres uses this guy. Again, this is part of the GIST library, just like KD trees is. So you don't create it explicitly. You just say, you know, create index on this table using GIST, and you pass it the columns that's going to be for the 2 axes. Or you could pass 3 if you'd like to create an oct tree. Okay? Now again, just like in the case of KD3, whenever we use the GIST, we actually don't just pass the column name, but we pass an additional structure that tells the GIST exactly what we would like to construct. And again, I'm not showing it here. You can check the documentation that I have linked here in the 9.2 version of Postgres, and they talk about it, and you can, you know, check further documentation about how you actually pass this structure to get a quad tree created. Now, what remains of today's lecture, we're going to talk about 2 features that are not really indices. They are extensions of the idea of indices, or special way to create indices, if you like. And they are very specific to Postgres, although other databases are you know, trying to support them. And I will show you a list at the end of today's lecture of who's supporting what. The first thing we're going to talk about is this notion of a partial index. Now let me show you first how you actually create a partial index. You would use the create index statement, the one we were looking at several times before. So you say create index, you give it a name on this table, on these columns, and then using this data structure, whatever you'd like, you know, b+3, hash, and so on. And you say where, this is the new part, and you put a where clause. Now, what is the effect of putting a where clause here? The effect is like this. The database engine is going to run this first as a query to select the rows that you specified a condition in the where clause for. So you say where x greater than 5. So you only retrieve rows or get rows out from the table where x is greater than 5. And this result set is what gets passed to the index to create an index on only this subset of the rows. So instead of creating the index on the whole table, you can create an index on a subset of the table by specifying a where clause where the where is actually, where the where clause is a condition that the row must satisfy to be passed to the index so that its value gets inserted in the index and it is, you know, available in the index. Okay? That's why I say here, only those entries matching the where clause will be included in the index. What about the other ones that don't match the where clause? They will not be inserted into the index. Now this sounds like strange, because if you'd like to build an index, you're building an index because you're speeding up the performance, because you're going to get queries based on, or asking for values, or asking for rows that matches this specific column that you're building the index on. But now I'm telling you, actually, you can exclude some of them. And the rationale here is that you're not getting queries on those values. So you don't need to include it in the index, because you never, or you rarely get queries on those values that you're excluding from the index. The effect of this is that you're making the index smaller in size. So hopefully it will fit in memory, and hopefully it's going to be faster. So here's an example of, partial indices. Now the where clause here is just the where clause you've learned in your first database course. Anything that is applicable as a where clause is applicable here. So for example, I'm saying create index partial status on transaction table where the status is in A, P, and W. So I could have like millions of transactions, but I'm only interested in those whose status is A, or P, or W. I could have maybe 10 different statuses for transactions, but I don't care. I am only interested in speeding up queries where the status is going to be either A, P, or W. And for those, I'm going to build an index. So if the query comes like select star from, transaction underscore table, where status equals A, I'm going to use the index. Where status equal P, I'm going to use the index, or the database engine will use the index, okay? Or where, status equal W, again, the database engine will use the index. What if you get this query? Select star from, transaction underscore table where status equal X. You're not going to use the index. The database engine is not going to use the index because the index does not contain any entries for X. So what's going to happen then? The database engine will load the table itself and open it page by page, and will retrieve row by row to find out rows that has the status equal X. Because it cannot use the index, because X does not exist in the index. What exists in the index are rows, basically A, P, and W, and rows that has A, P, or W. Okay? Another example here in the next line, create index partial salary on employee H where salary is greater than 2,100. So I'm going to create an index called partial salary on the column H inside the employee table. But my condition is that the salary of the employee is going to be greater than 2,100. So any employee whose salary is greater than 2,100, I will retrieve that row, retrieve the age, and insert that into the index. But any employee who is taking less than 2,100, I will not insert his age into the index. So that's one type of a variation or a different way to create indices. Let's look at another type. This is called expression index. This is the second variation of indices. By the way, these are not new data structures. These are not new indices. It's just a different way to work with indices, if you like. Okay? Now, this is called an expression index. This is how you write it. You say create index, you give it a name on a specific table, and you insert an expression on a specific column. Here, the word expression refers to any expression you could write in the SQL language. Okay? Any expression that takes an input as a column value and returns out some output, regardless of what that is. Okay? Or what type that is. So here are some examples. Let's look at the first one. It says create index users on lower username. That's the name of the index on the users table, and then the expression is lower. I'm calling the lower function. So this is an expression. Calling a function is basically constitute a valid expression. And I pass it the username column in the users table. Okay? Now, this is actually one part that students always get confused about. So let's go really slowly here. We need to understand what gets stored in the index. And to understand that, let's read the next point. It says it will be used, the index I mean, by queries that have a condition on lower username. Any query where this expression lower username appears, instead of actually going and fetching the username and passing it to the lower function to get the lowercase version of the username, and instead of doing all that, we're going to go to the index and retrieve the result from there. Okay? In other words, what we are storing inside the index is the result of the expression. This is very much like the concept of memorization. If you remember from your Prolog days, this notion of storing results. That's exactly what we're doing here. Okay? Now, why this is useful? I've brought this example specifically because it highlights a problem we always face when you develop, websites. That any database engine is typically, case sensitive. So when the users type their username, they could type it with a capital case, especially for the first letter, and the rest small letters. But later on, when you ask them to log in, they will type it all in lower letters. So instead of giving the user an error message telling him that your username does not exist, what you do is you convert it to lowercase. This is what this function is doing. But that means every time you would like to, do anything with the username, you have to convert it to lowercase. That's a lot of computation wasted. Because every time, you do something with the username, including, for example, using the username as some kind of a security check, that if the user would like to do any transaction in your website, they would send you the session ID along with the username. So now you have to always, convert it to lowercase. Okay. So what this expression index involves is caching the result of the expression. So you don't have to compute it over and over again. But that means it's only used if the same exact expressions appears again. Okay? Because it is caching the result of a specific computation, of a specific expression. So if it changes slightly, then that's a different result. Okay? So I hope that was clear, and you will see some examples in terms of expression indices in the tutorial. Now, I have here a list and a link at the end of the slides that takes you to this page on Wikipedia, and I invite you to read it. I'm not going to ask you about it in an exam, but I want you to check it out because this shows you the variety of database indices that exist and who is supporting what. Okay? For example, I'm looking up here your SQL server. I think it's in the next slide, so let's move to that. And where is your SQL server which is the one you learned in database 1, is actually in the third row from the top. And here is what is supported and what is not. Now, it supports R3s, okay? It supports hash-based indices. It supports expression indices. It supports partial indices. It supports something called reverse indices, which we didn't cover. We don't have time for it in the course, but it's a simple concept, so you can learn it on your own later on if you'd like. It supports bitmap, which we discussed. It has no support for gist or gem. These are now becoming a standard, but SQL Server does not support them. It supports full text search, so it has support for full text, like searching in paragraphs using its own search and indexing technique, and it supports spatial indices as well. Okay, if you look down at somewhere in the second half, it says PostgreSQL. This is the one you're going to use for your project. This is the one we're using in the course, and the reason why I'm using it, as you see, it's all yes. It's the only one that has yes in almost all of them. Okay, so it supports a variety of indices. So go and check these guys. And by the way, if you read the second line from the top, it says information about indices other than basic B+3. You see, the B+3 is supported by all of them. Everyone has B+3s, okay, which you've learned in the early lectures. The question is, what else is supported? Because B+3s are really powerful because you can answer any type of query apart from nearest neighbor, because it's not made for that. And it will have usages that we will see later on towards the end of the course when we talk about concurrency and synchronization. Because if you have a B+3 index, you can actually enforce certain multi-threading features directly on the B+3 nodes. Okay, so we will come to that later on. Here are the references for today's lecture. I've covered quad trees, I've covered partial indices and expression indices, and this is the link that I was referring you to in terms of which database uses which index.